In this lesson, we're going to discuss curve fitting and polynomial interpolation. You may want to estimate intermediate values between precise data points. The most common method used for this purpose is the polynomial interpolation. And one of the most popular is the Newton's interpolating polynomial, which is a very useful form. The simplest form of interpolation is to connect two data points with a straight line. So this is known as the linear interpolation, and this is the formula. So f of x sub 1 is the value of y, at a given x sub 1, and then f of x sub 2 here is the value of y at given x sub 2. So this is also known as the point slope form of a line. Okay. We want to estimate the natural logarithm of 2 using linear interpolation. So suppose we're given x sub 1 equals 1 and then x sub 2 equals 3. So we want to find a value of y between x equals 1 and x equals 3. So let's say x equals 2. So what would be the value of y? So we know that 1, the ln of 1 is 0, and then the ln of 3 is 1.0986. So we will use a linear interpolation to estimate the value of ln of 2. So using the formula, okay, so we want to find f of 2, or that is your ln of 2. Now your f of x1 is 0, that is ln of 1, which is 0. And then your f of x sub 2 is ln of 2, which is 1.0986. So we know f of x sub 1 to be 0, and you have x sub 2, which is 3, and then x sub 1 is 1. So x is 2 here, and then x sub 1 is 1. Okay, and then computing this using your calculator, you will get 0.5493. And note that ln of 2, the exact value is around 0.6931, so which represents 20.7% error. So the huge error here resulted from estimating a curve with a straight line. So we know that logarithmic is a nonlinear curve. So this is the graph of ln of x, and this is the true value of ln of 2. And then we try to estimate using linear estimates. So the error can be reduced by a shorter interval as depicted in the figure. So if we reduce the interval, so this is the original one, and then if you try to reduce the interval, okay, the estimate will be closer to the true value. Okay, let's have a quadratic interpolation. So quadratic interpolation requires at least 3 data points, unlike in linear interpolation. So the formula is given by the following. So your a sub o is f of x sub o. So x sub o is the initial value. and then where a1 is equal to f of x sub 1 minus f of x sub o divided by x sub 1 minus x sub o. And then this is how you will get your a sub 2. So we'll be needing f of x sub 2 and f of x sub 1. Okay, so here we employ a quadratic polynomial in estimating ln of 2 using 3 data points. So we have we are given 0, 1, 2, or rather 1, 2.5, and 3. So we'll take this as your x sub 0. And this is x sub 1. And this is your x sub 2. So this is your f of x sub 0, f of x sub 1, and f of x sub 3. So this is ln of 1, ln of 2.5, and then the ln of 3. So this is your ln of x. Okay, so your a sub o or f of x sub o is f of 1, which is equal to 0. And then we compute for a sub 1. So this is your x sub 1 and then x sub o. So you will get 0.6109 for your coefficient a sub 1. And then for coefficient a sub 2, so your x sub 2 is or f of x sub 2 is 1.0986. So this is ln of 3. And then x sub 1, or rather f of x sub 1 is 0.9163. This is ln of 2.5. Okay, and computing, you will get negative 0.1232, and then we substitute in the quadratic formula, in our quadratic formula. Okay, so we already have a sub o, which is 0. This one is 0.6109. This is negative 0.1232. And then if we want to estimate ln of 2, okay, so this is the quadratic polynomial or interpolating polynomial. So at x equals 2, we just substitute. So 2 here, 2, 2, and then compute, you will get 0.6724, which represents only 2.9% error. So if you try to increase the degree of your interpolating polynomial, you also decrease at the same time the percent error. Now let's have Newton's polynomial. So the general form is given by a polynomial with n minus 1 degree. So this is a generalization of the linear and quadratic polynomial. So to find this new interpolating polynomial, we use the divided difference method that we discussed from the previous lesson. Now let's have another interpolating polynomial, which is the Lagrange quadratic polynomial. So here we want to fit a parabola through given 3 points using Lagrange quadratic formula. Okay, so the polynomial can be written as follows. So you're given x sub 1, so 3 data points, x sub 1, x sub 2, and x sub 3. And then the value of x sub 1 or the value of y at x sub 1 is f of x sub 1. This is the value of y at x sub 2, the value of y, f of x sub 3, the value of y at x sub 3. So given the data points, 3 data points, we substitute in the Lagrange formula, okay, to get the quadratic polynomial. So in this example, we use the quadratic Lagrange polynomial to estimate the density of unused motor oil at 15 degrees centigrade. So we are given the density at 3 given temperatures. So when the temperature is 0 degrees centigrade, the density is 3.85. And then when the temperature is 20, the density is 0.8. When it is 40, the density is 0.212. Now we want to estimate the density of the oil when x, or the temperature, is 15 degrees centigrade. So 15 degrees centigrade is not given in this data. So we will interpolate using quadratic Lagrange polynomial. Okay, so given your x sub 1, x sub 2, and x sub 3, and then your y1, y2, and y sub 3, and then we compute to get 1.3317. Thus, the density of the motor oil at x equals 15 is 1.3317. So let's remember that curve fitting is used to find a simple function to approximate a complicated function. An interpolation method estimates the values between known discrete points. Extrapolation technique estimates a value of f of x that lies outside the range of set of values of x. Some transformations, such as logarithmic transformation, can be used to represent the data where linear regression is applicable.